After I had created that linear regulator with the Raspberry Pi Pico, I realized that I could create an electronic load using the exact same circuit. So I thought about it a little bit after I was playing around with the current sense resistors that I bought that weren't really doing all that well. And then I figured out that hooking up these two 3 ohm resistors here gave me an effective 1.5 ohm resistor, which was a lot more useful for the target currents that I'm looking at. For example, if I have 1 amp of current, I would expect a 1.5 volt drop across these resistors, which is great. I can go up to 2 amps and I can effectively measure that current using my Raspberry Pi Pico. So what I've got here is the entire circuit from the linear regulator, just slightly modified here. So I'm still using the 12 volt gate driver logic here. Remember, we had a PWM output that we smoothed using an RC circuit there, and then we ran it into an op amp to multiply it by 4 to get it up over 12 volts. This is the gate here. And then the drain we have connected to 12 volts, and then the sink we have routed through these resistors, and then those resistors go to ground. With this circuit, I can make basically an electronic load. I can vary the gate voltage here, which varies the current through here, and then I can measure the voltage across these resistors that measures the current through the entire circuit. And then I can target a particular gate voltage level to get the current that I want. So what I've done is I've slightly modified this program to target a target amps instead of a target voltage. Now it's still measuring voltage because that's all the Raspberry Pi Pico can do. That's all I can do with this. With my analog to digital inputs, all I can do is measure an analog voltage effectively. So I've still got to measure that voltage, but my target is an amperage. Every 1.5 volts of that is an amp. So if I have 2 volts, or if I have 3 volts, that would be 2 amps. If I have 1.5 volts, that would be 1 amp. I've hooked up the oscilloscope just to measure a couple things because it's good at just dynamically measuring them. It also will tell me a little bit about the dynamic nature, like how long does it take gate voltage to get up, if there's any oscillations, those sorts of things. But I've got my yellow lead connected to the voltage across the resistors, so this should tell me basically the same value that the Raspberry Pi Pico is measuring. And then I've got this lead connected to the gate voltage. So that's the voltage that's going to the gate of the MOSFET here. And I've got my giant heatsink here because I need it. Played around with this and I can dissipate over 20 watts, and this heatsink gets quite hot. We've wired this all up, and I'm just, where I try this, I'm going to set the amp limit on my power supply down to a half amp. And so we got it at 12 volts. The current limit is 0.5 amps or 500 milliamps. And hopefully if anything goes wrong, then it won't be that big of a deal. I'm going to target 0.25 amps. So let's go ahead and turn this on, and you'll immediately see, wow, the oscilloscope is going wild here. So that's not good. You can see we current limited here. So we're up to our half amp. So that means something went wrong. Oh boy. You know, it's currently, oh boy, look at the look at the oscilloscope there. It's really hunting. That's that was pretty. I feel like I've got something wrong in the circuit here. So, oh, there we go. Oh, perfect. Okay. Great. So apparently the Pi Pico just was not installed very well in there. The PWM frequency is much higher than what I was using previously. I think this results in less noise. Now you notice here, when I had 50,000 hertz, these lines were very fuzzy and they were bouncing around quite a lot, almost like a volt. And so they're much more well defined here at 250 kilohertz. So there's less, I guess, I'm not sure you'd call this ripple, but noise in the circuit, or just kind of oscillations around the target. You can see on the oscilloscope, the max is 320 millivolts across these guys, and the max on the gate voltage is about 4.3 volts. We're actually maintaining a consistent load. So we're measuring 320 millivolts across these resistors. If we divide that by 1.5, remember Ohm's law, and these two 3 ohm resistors in parallel are equivalent to a 1.5 ohm resistor, we get 2.13. So again, within that correction factor, we're relatively close to the actual amperage that we can see here through the circuit. Let's allow 2 amps through here. So the program, this PID feedback loop that I wrote for the linear regulator and adjusted slightly for this electronic load, it's not going to use that 2 full amps because remember I told it to target 0.25 amps or 250 milliamps. I can come back into this program, go ahead and go for 1.5 amps. So our output's going to reset. You see very quickly, you saw the oscilloscope as well. So you can kind of see when I turn this off, watch the oscilloscope, you can see those values go down. And then when I turn them on, they very quickly stabilize at the target values. And very quickly, you can see the amperage through the circuit goes to 1.5 amps. We're dissipating 18 watts of energy through this MOSFET here. We're going to let that get heated up a little bit, and then we're going to see if we can capture that on my IR camera here. You can see we're getting up to about 180 degrees Fahrenheit, and if we look at the rest of our circuit, you can see the Pi Pico isn't terribly hot. You can see those load resistors, though, are getting pretty toasty. He's quite hot to the touch now, very, very hot. What I want to do is I want to push my luck a little bit, and let's see. Let's go ahead and let's do 3 amps. Yeah. Okay. So again, we just changed the limit on the bench power supply. We didn't change the amount that the program is told to consume. Go ahead and edit that. Let's do 2.5 amps and see if we can hit that. The gate PWM was 45% for 1.5 amps. Oh boy. Oh no. That's not good. that was not good at all. The PWM is just bouncing all over the place. The gate voltage is bouncing all over the place. The current is bouncing all over the place. It's not good. That's let's just try like 1.9. Okay, great. So it settled down at 1.9 just fine. So I'm not exactly sure why 2.5 is a bridge too far. So let's sneak up on it a little bit. Let's try, I don't know, 2.0. Not get greedy. I got 2.0 just fine. You can see we've got it here. So we're up to 24 watts. Let's do 2.1. 2.1 just seems to be a bridge too far. It might just be that whatever the PID factors I have, they're really just working in a regime of lower current. So I'd have to go through and tune these PID factors to work at this higher current regime. So let's go back down to our limit. It looks like it was about 2 amps is the most we could do here. There we go. Now we're dissipating 24 watts through here. See if things are getting much hotter. Roughly 200 degrees. So you can get this hot enough to boil water. It's still not, again, this is an automotive MOSFET. It's designed to go much higher than that. So we're not really in any bad shape. This is fascinating and all, but like all I'm doing is like heating up some resistors with a bench power supply. Like, why is that at all interesting? Well, what people do a lot is they use a programmable load to just discharge lithium-ion batteries, discharge lead acid batteries, cycle a battery to test their capacity, just to drain the battery so that you can charge it up all the way, put it through a full cycle. I have an 18650 battery here. This is probably the cheapest piece of crud you can find on Amazon, and I made the mistake of believing that. So it says this is a 99 milliamp hour battery. So one thing we could do with this load is just charge it up and test that. So I could set this load to take out a set amount of current and time how long it takes for that and actually measure the milliamp hours that it has. I guarantee you it's probably more like 1500 milliamp hours. It tops maybe 2000 milliamp hours if I'm lucky. So I got taken when I bought this battery, but we can leave this circuit almost identical. We still need to power the MOSFET and the op amp with 12 volts, but we can run the battery voltage across the gate and the source. So we leave everything else here the same, but we take the positive lead off the bench power supply so that we're not driving 12 volts directly into this anymore. And we plug the positive lead from the battery into here. And I've got a little switch here so I can control if that turns on and off. So it's going to be off by default. And then we plug the negative just into the shared ground. Now I don't want to pull 2 amps from this battery, so let's go and put our target amps back down to like 0.1 just to start. Now remember, we're not actually going to be drawing any current through this power supply anymore, so the amperage here is not going to show us anything helpful. That's kind of fun. You can see the gate voltage is just sweeping through its entire range. I'm not sure why it's doing that. I mean, it's obviously not getting the amps that it's looking for from the battery. Oh, because I didn't turn the battery on. It says I'm pulling 1 amp of current. That's not great. Oh, it just stabilized properly. I don't know if maybe I had something shorted when this guy was sitting down here. This is a very, very touchy little setup. This is awesome. You can see we're actually pulling 1 amp from our battery. I'm not so sure I'm very interested in the gate voltage anymore. I'd actually be a little bit more interested in the battery voltage. So let's clip on to the positive lead here. So it says it's got 3.6 volts here at 0.1 amp output. Resistors aren't really pulling a ton of, boy, they're still hot. So you can see over here, we're not pulling hardly any amperage here because all we're doing is we're running the op amp in the gate of the MOSFET. It's really the battery that's dropping current through the MOSFET, not the power supply. Let's go to 0.25 amps on the battery. Awesome. Woohoo! Okay, so we're back up to the 320 millivolts that we had before. We see the cell voltage has dropped a little bit. It used to be 3.6, so now it's 3.5. That's what you expect from battery. If you pull more amps from it, its battery voltage actually goes down. Let's push our luck. Let's try a whole amp. It seems to have worked. And you can see the voltage here is down to 3 volts, which is pretty low. If you read the information on the battery, I think it warns you not to take the battery below something like 2.97 volts, or something like that. We've used this programmable load to effectively discharge a battery at a 1 amp rate. It's not feeling too hot. We could probably even go higher than that. I don't think I want to mess around with that. But basically, now I've kind of reverse engineered this guy. So I could build my own little homebrew electronic load. One of the things I would probably want to do is have a little spinner knob, a potentiometer that dials up a particular amperage like this one does here, and have a display that actually shows the math of the amperage that is calculated. So I could imagine printing up like a little 3D case for this, soldering this all to like solder board, something like this, or maybe even making a PCB. It would be fun to make a PCB to do this. Although I think the Raspberry Pi Pico is definitely a huge amount of overkill for a project like this. So thanks. This has been a little foray after I had created that linear regulator with the Raspberry Pi Pico. I realized that I could create an electronic load using the exact same circuit. And I think that I could actually do this with the switch mode power supply that we're going to build in the future. Instead of targeting a voltage, you could target a voltage across these resistors and therefore target an amperage. Now, I'm not sure that makes sense with the switch mode power supply because the whole idea of a switch mode power supply is to be more efficient and to not bleed off electricity as heat. Whereas the whole idea of electronic load is to bleed off electricity as heat. So I think this is actually a great use for a MOSFET, using it not as it was intended, but it is a great way to bleed off a targeted amount of electricity is heat. It's just not a great way to do that in a high power power supply. Oh boy, we're getting some little shakes in our voltage here. It could be the battery is dying. I think the battery is dying. Oh, I might have killed my battery. Yeah, the battery without a load on it is now down to 2.4 volts. So I think I might have killed my battery. Well, luckily I can use the bench power supply to try and charge it back up, and we'll see how that goes. I don't think I've done any. As long as it's got some voltage on it, it's probably retrievable. And you can see it's kind of cool. It's actually recovering over time as we watch it. So there's some chemistry going on in there internally. Well, thanks for watching. Thanks for watching my little experiment to create a programmable load using power resistors and a MOSFET.